Assalamualaikum warahmatullahi wabarakatuh. My name is Astrinta Sharibulan as the first speaker in my group. So in this video I will to explain about the Euclid's number theory. Euclidean divisibility properties. Also, Euclid's great work entitled Elements Geometry, the subject matter extends far beyond what we now think of as high school geometry. This Euclid number theory is in the 7th, 8th, and 9th book of the Elements of Euclid. A definition: an integer b is said to be divisible by an integer a not equals to 0. In symbols, a divides b if there exists some integers c such that b equals ac. One writes a divides b to indicate that b is not divisible by a. So, from this definition, we can take the following example, that 39 is divisible by 13. Because 39 equals 13 times 3. However, 10 is not divisible by 3, for there is no integer c that makes the statement 10 equals to 3c is true. This is the following. The following is Euclidean divisibility theory. You can see the following equation in this. Next is the algorithm of Euclid. Division theorem. For integers a and b with b greater than 0, there exist unique q integers q and r satisfying a equals qb plus r, where r greater than or equal to 0 and less than b. The integers q and r are called the quotient and the remainder in the division of a by b. We accept the division theorem without proof, noting that b is a divisor of a if and only if the remainder r in the division of a by b is 0. The division theorem can be used to determine the GCD value using Euclid's theorem. In what way? By using the following system of equation. You can see the following equation. For more details, I will to explain about an example of determining GCD using Euclid's theory. Find the GCD value of 105 and 60. Before doing it, we must remember that we are using the following equation. First, we look for 105. Now, this 105 get the result that 1 times 60 plus 45 equals to 105. Why 60? Because if we look at the previous equation, this equation, b equals aq1 plus r1, where b is 105 and a is 60. Why is 60 multiplied by 1? Because if we take 2, the result will be greater than 105, which is 120. So we take 1. Then the result is 60. 60 plus how many will produce 105, which is 45. So we take the value into the equation, then 105 equals to 1 times 60 plus 45. And continue with the equation, this equation. A equals to R1 Q2 plus R2. It is known that A is 60, so it is the same as the previous one. And so we just memasukkan the value where we got that A is 60 and R1 is 45. Since 2 times 45 is greater than 60, we take 1. 1 times 45 equals to 45. 45 plus how much it makes to 60? 45 plus 60. 45 plus uh, 15. For 45, 45, 50 times how much make 45? The result is 3 because we have found the result of 45, then it's just here. Then it is add by 0. So the GCD of 105 and 60 is 15. Next is theorem. For integers a and b of which both are not 0, there exist integers x and y such that GDC AB equals ax plus by. Another theorem is let a and b integers of which both are not 0, then a and b are relative prima if and only if there exist integers x and y such that 1 equals to ax plus by. Next is corollary. Corollary 1 is if GDC AB equals D, then GDC A divided D, B divided D equals to 1. Corollary 2 is if A divided C and B divided C with GDC AB equals to 1, then AB divided C. Yes. Next is the fundamental theorem of arithmetic. Every positive integer n greater than 1 is either a prime or can be expressed as a product of primes. This representation is unique apart from the order in which the factors occur. Next is theorem, which reads, if P is a prime number and P divides AB, then P divides A or P divides B. The proof is, if P divides A, then we don't need to go any further. So let's assume P not divides A, since the only positive divisor or P, therefore the only candidate for the value of GDC AP are 1 and P itself. This means that GDC AP equals to 1. Quote Euclid's lemma immediately after P divides B. This time you are probably an infinite of primes. By this time you are probably asking, is there a prime number that is the largest, or do the primes go on forever? The answer is to be found in a very ingenious yet quite simple proof given by Euclid, or Proposition 20, Book 9, in his Elements. In general terms, what he shows is that beyond h prime another and large prime can be found. The actual details follow. The arguments is Euclid's, although the words and modern notation are not. So I think it's enough for me. Thank you.